Today I present the work that I have been developing with Didier at EPOC, University of Bordeaux, since November. So it's a work in progress. But the title is Critical Salinity as an Early Warning of Tipping Points in the North Atlantic Subpolar Gyre. So in this work, we are interested in the tipping elements in the SPG, the drivers of this process, and possible to find some thresholds to work as an early warning. So what you are calling a SPG tipping event here, it's a very fast cooling event. So the criterion that you're applying, you're calculating the sea surface temperature anomaly in the P control, and do the same, and we do the same in the future scenarios. And when the variability in the future scenario is 3 times the standard deviation from the P control, we are calling this tipping point. So this is the same methodology that was applied by Zgubin and Zwingedo. We are using this in SEMIP6 models as the work in Didier, so I end up with the same models and the same scenarios from his paper. It's these 3 models. And you can see in the blue line, this is the SST in the subpolar gyre. You can see this fast decreasing. It's the tipping point in each of these models. In this last one, the NORSM2LM, there is 3 tipping points. There is a decreasing the SST, a recovering, a decreasing, recovering. And the other 2 is just 1 tipping point and keep the SST in this pattern. So to investigate this, the first thing that we did was plot the properties by depth in this region. So here I'm showing you it's the density, temperature, and salinity from surface to 2000 depth. The colors is the mean decadal value. So it's going from blue, from the most recent decade in the SSP, the future experiment, from 2015 to 2024, and going to yellow, that is the end of the 21st century. So this is one example with the SASM2 WSCCM. It's one of the models that it's presenting a tipping, but in the other tipping models, the pattern is quite similar. So the salinity is freshing in all depths. However, the trend is higher in the surface, so it's freshing more. The temperature, the pattern is a little bit different. It's cooling in the upper levels, in the upper 215, about this, and it's decreasing the surface, as we expected, because it's what they are calling the tipping in these models. But the intermediate layer, it's warming. And the density, this is a region that the variability is most driven by the change in the salinity. So the pattern, it's following what is happening in the salinity. It's decreasing, the density is decreasing in our profile, but it's decreasing in a higher trend in the surface. So this makes the water more stable. This increases the stratification. And what our theory is that this higher stabilization that is being driven by the fresh signal in the surface, it's decreasing the mixed layer depth, stopping the convection in this region. And this is what it's resulting in this pattern in the temperature, that it's cooling the surface and warming in the intermediate layer, because this is the pattern that we expected that happen when the convection is stopping in these regions. So to investigate this theory, to confirm this, we want to test this critical salinity theory that is based in, again, in the convection and in breaking the stability. So to break the stability in a region, the density in the surface needs to be equal or higher than the density in depth. So here we are applying in 1,000 meters, but we can do this. We did some tests with 500, 2,000 meters, and the pattern, it's very similar. So to have this as affirmative, to confirm this, we can have the variability of from the surface to the deep. You can write this as a function from the variability of the temperature in the surface, and the temperature in the depth, and the salinity in the surface and the salinity in depth. Of course, weight by the coefficients, the alpha and beta, the aline and thermal coefficients for salinity and for temperature. So from that, we can, this equation needs to be, where is this? This is the point. OK. So these will need to be higher than 0 to confirm that we are able to break the stability. We are interested in finding a salinity surface threshold that will make this assumption true. So we isolate this saline surface, and we end up with this equation. This saline surface, when we are equal to this is what we are called the threshold for the critical salinity. So we enter from the model the depth, the salinity in the depth, so in 1,000 meters, the temperature in the depth, again the same depth. We calculate the alpha and the beta coefficients, and you're using the temperature surface in the frozen point, less 1.8, because in these regions, it's happening, the convection happens in the winter when the surface is very cold, and you're being very conservative because the temperature is helping to break the stability. So this is its most conservative value to find a threshold for the critical salinity. So we apply this for the SEMIP6 models in every grid point, and we can end up with two different scenarios. The first one, the sea surface salinity will be higher than the critical salinity. So in this case, so the profile here in the surface, the salinity is higher than this critical value that we calculated. In this case, the ocean is able to break the stability during the winter. So the mixed layer depth, it's deeper. And we have exchange during the winter between deeper waters and the surface waters. This is what's happening in the real ocean during the late winter, and it's what's happening in the tipping models during the historical experiments. The second scenario is when the sea surface salinity drops below the critical salinity. In this case, the ocean became too stable. The stratification is too high, and it's not able to break this stratification during the winter. So the mixed layer depth, it's shallow. There is no exchange between the surface water and the deeper waters. And this makes the tendency to decrease the temperature in these upper levels, and even could formate more sea ice in this case. So we want to confirm this, so we test this in the tipping models and in some no tipping models from SEMIP6. So here, I calculate the difference from the sea surface salinity and the critical salinity. And I plot these maps for decadal average. So in blue, it's where the sea surface salinity is smaller than the critical value. In this is the case where the ocean is not able to break the stability. So this is from SESM2 WCCM, one of the tipping models. In the beginning of the future scenario, the blue signal, it's just in the west coast. Close to the Labrador Sea. There, and in the center of the subpolar gyre, the difference is very high. So it's in this period, during the winter, the ocean is able to break the stability. But in the next few decades, this difference starts to decreasing until this decade, where the blue signal it's expand to east, and the center of the subpolar region, it's close to 0 or negative. And this is when the tipping happened. In the next few decades, this negative difference is expanding east until the end of the century, and this differences dominate the subpolar gyre. So this is the same period, the same average, but for mixed layer depth. As we expected in this first mean decadal average, the mixed layer depth, there is deeper mixed layers in the Labrador Sea, in the Omega Sea, but this is decreasing in the next few decades until the period of the tipping, where this is almost disappear in the subpolar region, and in the end of the 21st century, this is a complete shutdown of the convection. This is just one example of these three models, but the other two, it's showing the same pattern. So here is a video where the map showing here is the same difference from sea surface salinity to critical salinity, but now I'm showing annual average. It's starting from the historical in the 60s and going to the future scenario. And in the bottom, I'm plotting the area inside this black square, in the subpolar region, where the difference is negative. So it's where the sea surface salinity is smaller than the critical value. So during the historical period, we have some annual variability with the variability in the CA surface, but not exactly, there is no a trend during this period. But now we enter the future scenario, and it's approaching the tipping point, is 52, and now it's the tipping point. And this is start to dominate by this very negative area until the end of the 21st century. And it's not recovering. So here I plot the mean values of the sea surface temperature, sea surface salinity. So in orange, you can see it's the sea surface temperature in the subpolar gyre. It's going from the historical period to the future experiment. In green is the sea surface salinity for the same period. The blue line is the same area from the previous video. And the black is the critical salinity in annual average. In dark red and dark green, you can see it's from sea surface temperature, sea surface salinity from ISOs. So it's in situ data. It's what we are expecting from the real ocean. In this, here exactly in this period, it's where in this red arrow, the SST it's dropping very fast. It's the tipping point. And just the year before that, there is this very high jump in these areas. And at the same time, the salinity it's decreasing just before this tipping element is starting. This is said into WCCM, but in the other models with tipping point, the same pattern it's happening. This salinity is decreasing since the future scenario, and when this is passing by or approaching the critical value, it's when the tipping is happening, and we have these jumps in these negative areas. Even in the NOR-SM2LM, the same is happening when we have these three tipping points. The salinity is decreasing from the critical threshold and recovering, decreasing, and recovering these 3 times just before the tipping happened. So this can explain why the sea surface temperature it's tipping in the subpolar gyre. 3 minutes? Okay, thank you. And what is happening in the models without tipping, the no tipping models? I test about 15 models. This is one example. Most of them presenting the same pattern. Usually they are too cold or too fresh or both. This model here is too cold and too fresh since the historical period. So as you can see from this is ISOs is what we're expecting the end of the historical period. And this is critical salinity, it's black line. And the sea surface salinity is much below this value from the historical period. So it's tipping before the future scenario. This is happening, this is the same pattern in most of the other models. There is just 2 other models that it's no tipping. And instead of being too fresh, they are too salty. So the salinity is too higher and they are decreasing in the future scenario. However, they are never going close to the critical point. And in the real ocean, how far we are from this critical threshold. So I plot here is from N4 and ISOs, that it's composition for Argo floats. So it's the real ocean. Again, in green, it's the sea surface salinity. In black, it's the critical salinity. And the blue, it's the area of the difference that I showed in the video in the previous figures. As you can see, we have some variability in the salinity since the 60s, but it's never approached the critical point. In the ISOs, that it's just 2002 to 2020, it's the same. Even when you consider these salinity anomalies, these periods where the salinity is dropping in the subpolar gyre, it's never going close to the critical point. We have these jumps in the areas, but it's not big as we can see in the models that it's tipping. So looks like for now we are, it's stable right now. The mean S critical for both is close to 33.8. So this is the threshold that we find from the tipping models, and it's the same in situ data. And yeah, currently we need to decrease about 1 gram by kilogram in the salinity, and the great salinity anomaly is decreasing just about 0.3. So even this anomaly is not able to decrease the salinity how it's necessary to stop the convection. However, this is a very fast process, so maybe if this starts to decreasing, this is just a few years and the decreasing, and we can shut down this process in this region. So the main message here, so the critical saline theory, it's quite simple, but it's important because it works in this region. The multimodal mean of the critical saline for the models with tipping is 33.8. It's almost exactly of the in situ data, what reinforce how these models is representing quite well the subpolar Gyre. The expansion of the areas where the sea surface salinity is smaller than critical saline precedes the tipping, so can work as an early warning. However, it's just in the year before, or when this happens, we know that in the next 10 years, the temperature is going to be decreasing very fast. So, but it's just in the start in the tipping, so it's not very early. And the current mean sea surface salinity in the SPG is 34.6. And so for now, this is stable. That's it. Thank you very much.